Hello. So I'm Joemon. I'm going to present our work on exploiting large language models as simulated uses to explore data space for reinforcement-based reinforcement learning-based recommender systems. This is the work of Wang, one of my PhD students, co-supervised by Ioannis and myself. G, as you know, unfortunately couldn't come here due to visa issues. So, let me first introduce the problem and tell you what we did, and then I will explain how we did it. So the problem is, as many of our previous authors presented, is sequential recommendation. Reinforcement-based learning and recommender systems are very popular. So the way these systems are trained using logged data, but when you do log data for reinforcement learning, the exploration of the data space is limited, and that will lead to suboptimal state representation. Now, a solution we come up with is exploit large language models as an environment. In other words, a simulated users which we can use to explore large data spaces. So what we did, to give the highlights, we fine-tuned an LLM as an environment. In other words, is a simulated user using a small subset of user interaction data. Small means 10% of the data. We could get a very good performance. This led to development of a robust state space as well as a reward model. Then, in addition to this, we use this fine-tuned environment to explore additional data spaces. So when we use reinforcement-based learning in online scenarios, users give feedback and the model get updated, right? But that is not happening in the recommendation scenarios because we cannot get expose users to suboptimal recommendations. So this led to, so what we did here, we created an LE and we used that to explore those collection, which further led to very robust performance. Now, LLMs are used in recommendation scenarios a lot and with very good performance. But one of the problems of LLMs is its inference cost. At the inference time, we have to deal with the billions of parameters. But our approach led to much more robust, leaner models. Okay, now let me explain how we did it. So our problem is session-based sequential recommendation, right? And I don't need to explain it, all my previous authors did that. So this can be, here a recommender can be trained using a supervised model. So for example, GRU, CNN, transformer-based models are exploited here. So what we did here, normally, so given an interaction history of a user, these models are used to encode a hidden state, which is then mapped to generate the logits for recommendation purposes. So we can, through this, we can basically analyzing the interaction data, we can create the hidden state, and then we can use create these logits for recommendation purposes, which is very, very effective. But then there is a limitation here, the way we construct this hidden state, because from the interaction data, which is very sparse. Now, reinforcement-based learning systems are used where the environment, given a state of an environment, agent is learned to create actions with the maximizing an objective of long-term return. So this approach found to be very, very useful for recommendation purposes, session-based sequential recommendation, because it allows flexible reward setting. We can consider novelty, diversity, etc. into the reward setting, and in addition, it optimizes long-term objectives, like what will be the return in terms of over a long time, which is very attractive for e-commerce settings. So one of the state-of-the-art works on exploiting reinforcement learning-based recommender system is supervised actor critic for recommender systems by Zinsin, published in Wisdom 22. The way they do is they train a model, reinforcement learning model, which shares a hidden state with the supervised head. And this, it uses Q-learning to update the states as well as optimize a long-term reward, right? Now, so there are two frameworks proposed. One of them is SNQN, Supervised Negative Q-Learning Network, and another one is SA2C. So here, it uses the supervised head, and also it uses the Q-Learning with the negative sampling to update the hidden states and generate the recommendation. And it also considers another framework in the actor critic mechanism, where the supervised head is considered as an actor, and it is weighted with the Q values from the critic. Now, this is a kind of state of the art. Then, what is happening here is we are sharing a hidden state between the supervised head and our agent. Now, this hidden state is modeled from the log data. So in the log data, we have interaction sparsity. That means because when you consider log data, the users are not giving feedback on all the data. So that's the data sparsity. This leads to affecting the quality of the environment. In other words, the space as well as the reward model we are building from this. Then another issue is the reward sparsity. What does that mean by reward sparsity? Is when considering the reward, we often consider, let's say, purchase is 1 point and click is a 0.02 weightage. And this kind of fixed rewards often lead to fail to capture the nuances of the user behavior, right? So as a result, the state or the hidden state we are forming using these models often lead to unstable states. So what's our proposal here? So we consider this and we are extending this along with a simulated user or a LLM-based environment, right? So which has two components, a modeling state model and a reward model. So in reality, we have two proposals. In addition to this, we also use this simulated or the LLM-based environment for exploring additional data spaces. In other words, that is not in the log data. So these together basically leading to generating a recommender system which can do good user feedback, updating states and rewards, and also we can explore it to simulate an online environment to get the feedback. So now let me explain how we did this. The first step involved in this process is using embedding. So item tokenization. The traditional approach is when you have an item information, we run it through an embedding process and we get each token embedded. But one of the problems when we are using LLM, the space may be used for the embedding and the LLM's underlying embedding distribution may be different. So what we did is we used something called a tokenizing item using a prompt like this. We have use the titles of the information run through the LLM prompt base, and we got an embedding of or a token for that item and information. So once that item is tokenized, we use that token for the further processing. Now, how do we do the state model and the reward model? So reward model is created using a prompt. So we use a prompt like PT80. The PT is the user has listened to this track in chronological order. User interaction history tokenized through the LLM is presented. Now the second component of the prompt is compute the likelihood that an item be next track listened to be based on the listening history. This item has two items on it. One is a positive one, the correct one user seen, and another is negative sampled item. So we use a score head on the LLM to fine-tune a reward model, right, using this loss function. Details are in the paper. We use the negative and the positive information for building that loss function. In addition, we also look into building a state model using this tokenized item information and also using a contrastive learning mechanism. So these are using this loss function, and these two, both the score head and the state model, optimized together with the LLM. So this led to the simulated user environment or LLM-based environment, okay, where we have a reward model as well as state model. Now, how do we do the recommendation? So now what we are happening is we got one hidden state from the supervisors and the RL agent, and also we are getting a state from the LLM as an environment. So we concatenated them. So state space is much more robust in a sense that we have information from both the log data as well as from the LLM. Yeah. Now, once that is there, and we have a reward model as well, so once we have there, we only need to use the baseline, the supervised actor critical model as a recommender. So that means we have two loss functions. One is cross entropy, and another one is using a negative sampling, which we are using from the baseline, the SNQN or SA2C model framework I mentioned before. Now, second component, in addition to using LLM as an environment, we are looking at exploring simulated online scenarios. So in other words, we want to use this to get feedback on items not seen by the model. So for example, what we do is we use the supervised head to generate a 5 rank list, and then ask the LLM to identify the item that the user may watch next. So this is the one not in the log data. This is an entirely new one generated by the superhead. So that's why the action augmentation problem. And we have again two loss functions. One is on the hidden state and one based on the Q-learning component. And these are optimized using a weighted component. Okay. So that's so once that is again a recommender is built, the two components. One is LLM-based environment, and another is the action augmentation, which help us to explore a simulated online scenario. So our experiments are done on music dataset, LFM, and Amazon Ruby dataset industry component, and our experiments are based on 4 research questions. Now I will explain this. So we are using SASREC and GRU, and I am showing the results of SASREC here. I'm using 2 datasets, and we use the hit ratio and NDCG at different 5, 10, and 20 points. So the normal means we are using SASREC as the baseline model. So the normal is using the SASREC, and SNQN is one of the reinforcement learning-based recommender frameworks, and SA2C is another one. And that's so you can see that when you look at this, the reinforcement learning-based framework improves performance, which is anyway the state of the art. Then what we do is we have considered different versions of our model. This LEAR means we are using the LE environment with action augmentation and reward modeling, or action augmentation and state, and all the components. So if you look at this row, you can see that overall the performance improvement with respect to the baselines are much higher. Okay. Similarly, that repeats for the SA2C frameworks also. This variations is much profound, and similarly for industry as well. Now, we also conducted the ablation studies. We looked into the LE as just a reward model only. So there is comparing to SA2C in LFM. So this LE uses only the reward model component to improve the SA2C, and it uses action augmentation as well as. So again, this improved the performance considerably. Similarly, the state model. So this means if you look at the state model, we are using the LE-based state model, the performance improved. This means a better design, reward, and state model can improve the performance of the reinforcement learning-based recommender systems. I will skip these. So this is a very interesting part, because we are using the action augmentation to just improve the baseline SASREC. So here the baseline models, here we are only looking at the improving the, augmenting the data with the feedback from action augmentation. And again, you can see that performance improved using the action augmentation component. So it again shows that in addition to the log data, action augmentation lead to a better performance. So let me conclude. So what we did is, we created an LLM-based environment which simulate a user, and then from that simulation we can create a better state model as well as reward modeling. We also looked into the creating an online simulated environment so that we can then again explore the performance, explore the data set much more than what is in the log data. And in addition, compared to LLMs, which always billions of parameters, we are only using LLM to train our baseline model, so that leads into a better and lean and robust model. That's all about our presentation, and thank you for your attention.
Any question from the floor? All right, I have a quick question. So for using the LLM, like the simulator, do you consider any kind of user characteristics?
Yeah, what we are using is users' initial interacted data, 10% of it, to train this. So it basically each user's characteristics it adopts. Then we can use this as a feedback tool.
Okay, thanks.
So for example, this experiment we did is varying that 10% of data, see, and we can get optimal performance with the 10% of that data. Okay?
Okay, thanks. Any other questions? Okay.
Thank you, Professor, for the great talk. So my question is, so when you are saying that we are using LLM as a simulator, so basically how we are evaluating it, like whether it's a good simulator or not?
Yeah. So that's interesting. So what we are doing is we are training our recommender model, and then we can do this evaluation, the performance of the recommender, given whatever be the data, given a sequence of interaction data, how much it will improve. So there are two components. We are using this log data for training this model, right? So which are varying. And in addition, there is an augmentation component is only one, is exploring new data. But when we are testing on the log data so that we know is it reflecting actual users' preference. Okay, thank you.